So welcome back, and now let's jump right into how these autonomous race cars are built and how do they work. In this lecture, we'll cover the basics of perception, planning, and control in the context of our race car. Next, we will introduce ROS, which is the software system that is used on this car. And then finally, we'll head over to practice session 1, where you will control the car using your computer instead of a remote control. Our autonomous race car is built using the 1/10 scale RC race car chassis, much like the one shown here. That is made by a vendor called Traxxas. As you can see, this car is more than just a RC toy. It is a very realistic representation of a real race car. It has a 4-wheel drive and it can reach top speeds of up to 40 miles per hour, which is really fast for a car of this size. This car consists of the following electronic subsystems. We have a high RPM brushless DC motor which provides the drive to all the wheels. Then we have an electronic speed controller, or the ESC, which controls the main drive motor. There's another servo motor for controlling the steering input. And the commands for the drive and the steering are received from the RC remote by a radio receiver. And of course, there's a battery pack which provides power to all these electronic subsystems. As you might have already guessed, in order to convert this RC car into an autonomous race car, we will be directly controlling the main drive motor and the steering motor using an onboard computer. So we begin with this off-the-shelf chassis as shown here, and then add a variety of sensors to enable the first steps towards autonomy. These include a LiDAR range sensor, a front-facing camera, infrared depth imaging sensors, and inertial measurement units or IMUs. These sensors are interfaced with a powerful onboard computer, which runs the perception and planning algorithms and is also responsible for figuring out the speed and the steering commands to be sent to the race car. We are using the NVIDIA Jetson TK1 as the onboard computer for our race car. We use another microcontroller to send the steering and speed signals to the car and add additional batteries to power the onboard sensors and the computing platform. We also include Wi-Fi hardware on board so that we can get real-time telemetry data from the car, which is very useful for debugging during the code development process. So we began with the RC race car chassis, and after integrating all the sensors and the computing platform, we end up with this. It is already looking like a promising race car, but it's not quite ready to race yet. We are missing a very important piece, which is the software or the brains of our autonomous driver. The software will add intelligence to this hardware and convert it into the autonomous race car that we want it to be. The following diagram shows the system architecture of the race car. Based on what we have previously discussed, you are now in a position to easily identify the perception, planning, and control parts of the system. The perception system includes the sensors and the interface to the main computer and the algorithms to process the raw data from the sensors into meaningful observations. Here is an example of how the perception works for the LiDAR sensor. On the left, you can see the external view of the race car approaching a turn, or a T-section in this case. Notice also how a part of the corridor wall on the left is protruding outwards. The image on the right is a visualization of what the race car sees or perceives. It shows the point cloud obtained from the LiDAR as it scans its surroundings. It can also detect the protrusion in the wall on the left and the T-section in front. Data from other sensors goes through a similar process where it is processed to provide information to the car about its surroundings. Once the car knows where it is, it can plan where it wants to go, and this is done in the planning part of our system architecture. You see here an example of a car in the corridor and how we are using a cost mapping algorithm to plan ahead on how we intend to navigate that left turn. Knowing the car's position and the planned trajectory, we then compute the required steering and speed signals that will ensure that the car follows this planned trajectory. This is the control part of our system architecture. So I hope that you have a better understanding now of how we interface our sensors and the motor controller with the electronic subsystems on these RC cars. For the sake of completeness, the system architecture diagram here also shows the fact that a computer has wireless connectivity and that we can get telemetry data from our car in real time. So next time, we'll go into details about ROS, which is the software we use to implement the algorithms to carry out the perception, planning, and control.